Oh, I figured it.
Okay, let's get started. So we're in lecture 18. Just so everybody's aware, homeworks 1 through 5 are graded. Exam 1 is graded. I'm still working on exam 2. That's going to take me a little bit. There's a lot of calcs on that exam. Why do I have a second parentheses on reports distributed? That's going to bug me. Get rid of that. Okay. All right. So I just gave you the exam report from the lab exam. So lab, the Traverse exam. You all have the grades for that. Class as a whole did fantastic. Not really worried about that. I don't have any homework assigned today, but remember you have homework 6 that's due Monday. A couple of you have actually already attempted it, and that's great. I'm accepting submissions up through Monday, and the way I have it set up, it'll take the highest grade. There are probably some questions that you might have been a little unsure about, but today, hopefully, you'll be, after today's lecture, you'll be a little bit more certain about it. I want to begin today to talk about our second mapping application, which is Topo, and our Topo surveys. Oh, I'll put property surveys. This is topographic surveys. Man, this is what happens when you copy and paste. This is topographic surveys. Topographic surveys. But before we get into the Topo lecture today, because we're going to be doing Topo Lab this week, I want to talk about the outline between now and Thanksgiving break. Okay, we're going to do something a little different than what we did or what was done last year with the Topo and with the labs. So I want to kind of explain. Okay, this week we're going to begin the Topo Lab, and the Topo Lab is at least going to take probably 2 weeks because it's going to take a while to collect the data. Some of you might be able to collect all the data necessary this week, and that'd be great. But not only do you need to collect the data, but you need to draw it up in AutoCAD Civil 3D, and that's just it's not something we can get done in 1 week. Okay. So what I'm going to do is this. Okay. So I have 2 weeks set up for the Topo Lab. Okay. Topo 1, we'll say Topo Part 1, Topo Part 2. So today's lab, or today and Thursday's lab, is mainly going to be focused on collecting as much data as possible. Okay, that's the goal. And if you can collect it all, great. There will probably be a few groups that aren't going to be able to collect it all by the time lab ends. So what's going to happen is we're going to have to come back next week and continue to collect a little bit more. That's natural. Okay. The way the Topo Lab is going to work, though, every person, not every group, every person is going to generate a topo drawing and submit it. Okay. Now, what I decided to do, because again, I'm trying to hold to my goal of not having like as many lab reports and intersecting lab reports and homeworks. I'm trying to not have a bunch of stuff due all at once. This is what I'm going to do. The horizontal curve lab was initially scheduled to be for 2 weeks. I've decided to retool that a little bit and make it a 1 week lab. Okay. So what I'm going to do the week before Thanksgiving break is I'm going to say lab is canceled. Okay. And here's what I mean by that. We're not going to have like an in-person lab. Okay. But I'm going to require all the topo maps to be submitted by this Friday, by the Friday of that week. Now, you are going to be well equipped to start working on that next week. And if you get it done early, the topo map doesn't take that long to generate. If you get it done early and submit it early, like I'm going to open up the submission next week, and you'll have until Friday, November 18th or November 17th to submit it. So if you submit it by the early, then we have this lecture, and in terms of CD 241, you're done till we come back for after Thanksgiving break. Does that make sense? So again, I'm trying to not layer lab reports and homeworks on top of you all at the same time. Now, I mentioned that with the caveat, we are going to have a homework on horizontal curves due this day, and homework on vertical curves due this day. So we are going to have some homework assignments add up on us a little bit. The earthwork assignment, though, I'm not going to make that due until like after break. Okay, is that fair? Does that sound good? So today and Thursday in lab, we're going to be data collecting fools. We're going to be collecting as much data as possible because to do the topo, you need a lot of measurements. For example, in some of the Traverse labs, what have we done? We've done like 8 or 9 distance measurements. We're going to be doing like 60, 70. We're going to be doing a lot of shots for topo. So the more the more that we can get done today, the better. Today and Thursday. I say today, but I mean today and Thursday. Does that make sense? All right, any questions on that? Okay, so that's how we're going to handle that. And again, I think it's the same amount of labs, it's the same concepts, but the staggering and putting the lab due this day will work out. And what I'm going to do, I think, when we come back for pre-finals week, they're not calling it dead week anymore, they're calling it pre-finals week. But what we're going to do that week is we're going to do our plan reading too, but during that lab, I'll probably take a few of you out one by one or group by group, and we'll do some GPS work. Just have some fun with it. Does that sound good? All right, so let's talk about topo. Okay, let's talk about that today. All right, so let's talk about our second mapping application. I mean, I mentioned this in the pre-recorded lecture when we talked about property surveys, but when it comes to our job as land surveyors, I mean, ultimately, I think it would make sense that we're ultimately trying to generate some kind of schematic of the Earth. And so that really takes sort of two avenues, two ways that we can go about it. On one end, we're looking at it from a property description standpoint. We're trying to, accurately describe the boundaries of a given tract of land or area or whatnot. But then there's the other aspect of it, which is looking at relief, looking at contours. But let's be a little bit more general in our discussions. So, when we're trying to map a given area, what are we trying to capture? So, I would separate it into two main categories between natural and cultural. So, natural features in a given tract of land would be like vegetation, any rivers, any lakes, bodies of water, things like that. Cultural would be anything that we built upon the land, so like roads, railroads, bridges, buildings, stuff like that. But also we would be interested in depicting surface relief, so the elevations. So, for example, we're in West Virginia, so we live in the mountain state, so obviously we're interested in determining where the hills are, where the valleys are, where the flat areas are, and so on and so forth. And there are multiple reasons for that in a civil engineering context. Number one, we need to understand the relief of the land in order to properly assess hydrology, to properly assess water runoff. I mean, part of our job as civil engineers is managing erosion and sediment control in construction projects, managing water flow in construction projects. And so we need to understand the relief of the land. For example, land that's like this versus land that's like that. This land, the water's going to flow a lot faster, and during a project, we need to be able to control that. The other big aspect of understanding, or another big aspect, I should say, not the other, but another big aspect of understanding relief is on the earthwork side of things. We'll need to understand the current lay of the land in order to properly assess the amount of cut and fill necessary for a given construction project. So there are multiple areas where this is really important, okay? Now, our common types of maps, though, are largely two-dimensional, and we're going to be focusing on topographic maps where it's a 2D map, but it contains surface relief, it contains contours. The property survey maps that we were looking at were mostly planimetric, where really all we cared about was horizontal positions between boundary corners and things like that. Now, the way that we depict relief on a map is through contours. That's the main way of depicting relief. So you've probably seen, everybody here's seen a map that has contour lines on it at some point or another. So you have the little squiggly lines, and what they're basically doing is they're indicating the change in elevation or the lines of common elevation. So just to make sure what we're saying, so for example, here we have sort of a 3D image, let's say, of a mountain or a mountainous region, and then up here we have a 2D topographic representation of the same thing. And so what these contours are essentially lines that circle a given map, and that line is indicating a known elevation, okay? And there are certain characteristics of contours that you can even sort of infer from this image. So for example, you can look at, let's look at, for example, like these contours right here. You can see the contours are spaced really, really close together. So what do you think contours that are spaced really, really close together indicate? A steep slope, yeah. So if you have contours that are spaced really, really close together, that indicates a steep slope. Whereas a gentle slope would be ones where they're spaced very, very far away, okay? So, and right off the bat, like that's pretty easy to understand. But there's also a couple of other things that are, that contours have characteristics of that we'll talk about a little bit later. Now, there's a couple of other ways that I do want to mention about developing relief data for a given tract of land, and I should mention a lot of the more modern techniques like photogrammetry or LiDAR, where instead of really trying to generate a map per se, you're sort of trying to generate a three-dimensional computer model that represents a given piece of land. And that's usually kind of important maybe in the construction side of things. For example, we have a lot of, for example, earthwork equipment where you can actually just sort of program the job into it and it'll just go and do its thing. So maybe in those environments, an actual map may not be all that necessary, although the science of what we're talking about is all very similar. I do want to mention LiDAR. LiDAR is a very common application for depicting relief and depicting surface contours. LiDAR stands for light detection and ranging, okay? And basically what happens is you have sort of you illuminate the target with the light, and what it's doing is it's essentially measuring the distance to and from that target, and it's calculating an X, Y, and Z coordinate for all of the associated points. So I don't know if this will play, but you can kind of get the idea is that as a given object moves, you can see, okay, we're generating X, Y, and Z coordinates for the point in question. And there's all sorts of different applications. For example, you'll see applications in agriculture, even in astronomy. You'll even see LiDAR applications in like law enforcement. For example, if you have a crime scene, you might use LiDAR to quickly map the given area. And LiDAR is something that's incredibly ubiquitous. It's so ubiquitous that you actually can see it present on your iPhone. So for example, for most modern iPhones, you'll notice that, okay, so if you look at the iPhone, that you see the three cameras, but some of you might not have noticed what's the deal going on with that black sort of circle there below there. That's a LiDAR, device. What it's usually used for is like, photo correction and whatnot, but you can actually use it as a rudimentary scanning device. Just to kind of give you an idea of how it works. So I have here the object here, and this is an app. I put the info for the app up here, but what I'm going to do is, let's see if you all can see this. I'm going to hit the record button, okay, and I don't know if you can see, but as I'm turning the camera, see how everything's red and then now it's not so red? Y'all kind of see that? So what it's doing is it's essentially shining that light, to a given point. It's collecting the distance data from that, and it's converting all of this into an X, Y, and Z coordinate. So what I'll do is I'll stop. That's enough for now. And so now what it's doing, you can see, now I've generated like a three-dimensional model just of the room, right? Pretty nifty stuff, isn't it? So now, is it anything that I would say is survey accurate on your iPhone? Of course not, But if you're just wanting like a quick, rough, model of a given space, you can do that pretty easily. So again, LiDAR's, pretty ubiquitous. You can find LiDAR technologies that are ground-based. You can also find aerial-based data collection. With any of these data collection techniques, the most important thing that, at least from a surveyor's perspective, that you need is to establish control. So for example, if you're wanting to collect LiDAR data, let's say down the street, well, you need at least some points that would indicate both magnitude and orientation. So for example, if I had two control points like here and here, and I surveyed those, if I knew the distance and orientation between those 2 points, I could use that to scale the LiDAR data such that the data that I collect is mapped to a chosen coordinate system. Does that kind of make sense? That idea kind of makes sense? So, but yeah, the app that I was messing around with is called 3D Scanner app. The icon has like a white house and like blue and red lines on it. So if you want to mess around with it, go ahead. So yeah, so as I was saying, you do need control for mapping surveys, and we've already been dealing with control already in this class, but again, we need a known reference. We need, and when we're looking at mapping surveys in particular, topo surveys, we need both horizontal control and we need vertical control. So horizontal control would be like 2 or more known points on the ground in order to perform resection to get X and Y coordinates. But we also need vertical control, and we've already even dealt with that in this class when we did differential leveling. When we're doing topo, you're doing all of it, okay? So for example, one of the things that, to be honest, we've been a little fast and loose with in our traverse labs is we kind of haven't, like, if you messed up the height of the rod, no real big deal. Well, that's going to be really important now, because if you don't have that data properly inserted, both the height of the rod and the height of the instrument, your topo is going to be off. So that's something that you got to get right. Okay, you got to get that correct for your topo to come out accurately. Okay, so let's talk a little bit about contour mapping. I want to talk about some characteristics of contours. I want to talk about some methods of generating contours. Just to give you kind of an idea of how this works, okay? So first off, I want to talk about contour lines. So what happens is surveyors, because of the tools that we have, we can collect what I'll call both planimetric data. And so when I say planimetric, that's just a fancy way of saying X and Y data, where I'm not worried about elevation. And for the most part, what we've been doing with traverses has been X and Y. We didn't really care so much about the elevation. I mean, when you all did exam 2, did we care about the elevations of those points when we were correcting? No, we didn't care. We were just looking at X and Y. Well, we're trying to worry, when we're doing contour, we're trying to worry about X, Y, and Z. Okay. Now, what is a contour line? It's a line that connects points of equal elevation along a given region. And a way of thinking about contour lines is, let's say that I have some hill or whatnot. Now, we're looking at this hill down here in profile view. This is elevation view or profile view. Okay? And imagine I took a big old samurai sword or lightsaber, if you happen to be a sci-fi fan, and I start slicing through the hill at even intervals. So for the example I've got here, let's say the interval is 20 feet. So we'll start off, let's say, at the highest one we can think of, 120 feet. So I samurai sword or lightsaber through the hill at 120 feet. And what do I see? Well, really all I see is just a little ring right here. If I were to look in plan view, what would I have sliced through? Just this little ring right here. So if you notice, the 120-foot contour is just that. It's just that little ring right there. What about 100? Well, if I slice through 100, I'm going to cut through this, but I'm also going to cut through this part right here. So that's why the 100 has this ring and then this one right here. And so you just keep doing that analytically, and then you generate your contour. Okay. What we have here are contours shown at 20 feet. It's not that uncommon when you're actually plotting contour maps that you might have your contours at 20 feet, but you might have darker ones at maybe, I don't know, like 100 feet to sort of make those a little easier to navigate, if that makes any sense. Everybody with me so far? Okay, so let's look at some characteristics of contours. These are some things that as you start looking through contour maps, you start looking at the nature of the problem, you'll find a couple things that have to be true about contours. So the first thing is that contours never end, and they must close on themselves. They might not close on themselves for a given mapped region, but ultimately they will, right? Because really all of the land that we're talking about on Earth really starts at the water and works its way up, like everywhere, right? So that's a part that's true. They never cross on one another. Whenever we're reading a topographic map, we assume that the slope between adjacent lines is uniform. So between line here and line here, we assume a uniform slope. As we were talking about earlier, the distance between contour lines indicates how steep a slope is. So if you got contour lines that are really, really close together, that's a steep slope. If you got contour lines that are far apart, that's more of a gentle slope. If you have contours that are kind of like this slide, where you have concentric rings that are closing together that increase in elevation, what does that represent? It represents a hill, right? So if you had the opposite, if you had contours that were concentric rings that were decreasing in elevation, that would sort of represent a pond or a lake, right? Because then the land is doing this, and that's where the water is going to collect, okay? Now, if you have lines of different elevation that happen to meet, the only way that can happen in the real world is if you have a cliff or you have maybe like a retaining wall or something like that. If you have lines that form a V that point upstream. Those are lines that are crossing a stream or something like that. And whenever you're looking at the way that water flows, look at the contours, look at them going downhill. The water flows at right angles to the contour lines going down. So you have contour lines going like that, the water's going to flow perpendicular to that. That's the way that gravity's going to want them to go. Does that make sense? Okay. So a couple things just to sort of like indicate what I was talking about. These are maybe some images that might help indicate that a little better. So this would be a situation where the hills the contours are concentric and they're increasing. So that's where we're talking about a hill. This would be where the contours are concentric and they're decreasing. And this is what I mean when I was saying that's probably like a pond or a lake or something like that. Okay. This would be an example of the what I was talking about with the contours forming a V and what have you. This would be sort of more of a valley type situation, whereas here where they're going up, this would be the line of a given ridge or a hill and whatnot that's going up. This is what I was talking about earlier when I said, you know, what is a situation where the contours could meet? Well, they might meet in a situation like this. So here you can see the contours are all sort of bunched up together. But what we've got is we basically have a wall or maybe a cliff or something like that. It's an abrupt change in elevation. That's really like the only time that could happen. Okay. Now, all right. Before I move on to like methods of locating, any questions so far? Okay. So, how do we actually generate a contour map? How do we actually do it? Okay, so theoretically, there's two ways of going about it. I'll call it a direct approach and an indirect approach. The direct approach is the bad way of doing it, okay? And that seems counterintuitive, okay? But let me explain how the direct approach would work. The direct approach would be finding points of a desired elevation and connecting lines around them to generate a contour. So imagine going out to Buskirk Field and saying, I need to find a point that has exactly 101 feet of elevation. So what you would do is you take a measurement. Oh, that's 101.62. I probably need to go down a little bit. Okay, let's take this one. That's 100.84. Okay, I got to go up a little bit. Until you found that point that was exactly 101, take that measurement and then do it again. And so it would be very, very time consuming to try and find points of a very specific elevation and connect the contours around it. That would be very time consuming. Instead, what's much easier to do is an indirect approach. So an indirect approach would be, okay, let's take Buskirk Field, for example, and let's split it up into a grid, okay? And for this grid, let's collect elevations at every point along the grid. And then let's interpolate between those elevations and generate contours. The contour will not be a theoretically, the contour map that you generate by this will not be a theoretically perfect contour map. It won't be 100% accurate, but it's very easy to do. It's suitable really for any terrain that you need to do, and it's much faster, okay? And so that's essentially what we're going to be doing in lab is an indirect method, and that's what everybody does. Much faster, much easier, okay? How do you actually go about doing that? Well, one of the most common field methods is to do radiation by a total station or a radial traverse, and that's what we're going to be doing here. So we're going to try and set up our total stations at a point where we can observe as many points as possible, do a resection in order to locate the total station, and just start shooting everything from that single setup. Don't move the total station. Just go here, go here, go here. Collect data, collect data, collect data, and so on and so forth. One of the nice things about it is most total stations are going to have onboard memory, which we're going to use in lab, where we collect the data on the total station and just spit it out onto an Excel sheet, which is exactly what we're going to do. The other thing about modern equipment is that you can code the points that you are collecting in the total station. So for example, you could say points 1 through 20 are all sidewalks, and then points 21 through 40 are all trees, and then points 40, 41, and 42 are courts or what have you. And so the nice thing about that coding is that we can import that into, let's say, AutoCAD Civil 3D, and it will interpret that for us and help generate the contours. Now, one of the ways that we can generate contours, and I'm just going to give you kind of an idea on how we would do this by hand, is what's called a grid approach, okay? So to give you, let me just sort of give you kind of an idea. So let's say I surveyed a tract of land, and let's say I split it up into grids. Let's say the space between these was 100 feet. So, oh my goodness, hope everybody's okay. So from here to here is 100 feet, 100 feet, 100 feet. And so let's say, you know, you set up your total station, I don't know, right here, and you had the rod person go here, go here, go here, go here. And every single one of those points you took a shot. And what you did is you measured the, you recorded the elevation, and now we've recorded it something like this. And so maybe what we'll do is we will try and generate contours. And for the sake of discussion, let's try and generate contours at a 5-foot interval. So we'll start at 740 and go to 710 or vice versa. And the reason why I'm doing that is because the biggest number that I see on here is like 743.1, so I can't do 745. And the smallest one I see is 707, so I can't go 705. Can anybody just look at this, this grid with these elevations and give me kind of a general idea of what you think the contour map's going to look like? It's kind of doing this, right? Like the elevations are really high here and they're really low here. So the land is doing this. So if the land is doing this, what do the contours look like? They're kind of going to go like this, right? And let me show you how that would work. I'm going to work backwards. Let's start off with 740. So the way that 740 would work is what I would do is I would take, okay, let's take this point and this point. If this is a common slope, where is 740? I don't know, maybe about right there? About like that? What about, is there a 740 here? In between here? What about here? Here. What about right here? I don't know, maybe about right there, right about in the middle? So the 740 contour line maybe looks like that. Okay. What about 735? Is there a 735 between here and here? Yes. About like that? What about here and here? Yes. Let's see. Tell me when to stop. Okay. Right there. Okay. What about here and here? Yes. What about here and here? Yeah. Big money, no worry, Yeah. About right there. Right? So that means that this contour line probably looks something like that, right? You see what I'm doing? See how I'm going through and I'm generating contours? And so what you could do is you could continue to do this, and you could say, okay, and typically what you would do is maybe break this and say, okay, this is 740. Maybe break this and say this is 735, right? And you would just keep doing that along the end until you got to the very bottom. And 710 would probably be, I don't know, somewhere like that. I don't know, maybe somewhere like that. So 710 kind of does something like that. Does that make sense? I'm not going to do the whole thing, but you can get kind of the idea how it would kind of go down in this fashion. Does that make sense? That's kind of like the classical way of doing it by hand. I'm not going to make you do that by hand in class, but I kind of want to just give you an idea of like how that would work. Now, imagine being in the field. It's a lot easier to do this than it is to try and survey these points because you'd have to go and find them, right? That would be very difficult to try and find points that have exactly an elevation of 735. That's a direct approach and it's very difficult, which is why we don't do it, okay? Does that make sense? Okay. Now, a couple things worth mentioning. So whenever you're performing your radiation by total station, so whenever we're, I mentioned this a little bit earlier, but I want to be clear on this. Okay, whenever you're collecting data in the field, specifically for a topo, what is incredibly important is proper note taking. Okay, and I'm going to give you some guidance in the lab this week, but this is one of those things where you all got to figure out your way of doing it yourself. Okay, so for example, if you collect point number 7. What is point number 7? Is it the southeast corner of the building? Is it this sanitary manhole and so on and so forth? You kind of need to track that, in a proper fashion, okay? typically what you'll like, so if we're looking at this, so typically we'll go through this in lab, but you'll want to collect data on your control points, your instrument setup, any utilities, trees, sidewalks. You'll then want to split up the land and try and do the contour grid and whatnot, try and get toes of your elevations, the tops of elevations, try and get data in between. The more data, this is one of the things, the more points you collect, the better. The more points you collect, the better the topo will look, okay? This is kind of an example of what I'm talking about. So for example, if I was, let's say I was looking at this house. So here's the house. I've got the house, I've got a sidewalk, I've got this curb right here, I've got 2 trees. And so when you're in the total station, so for example, point number 1, this is the northwest corner of the building. Point number 2 is the northeast corner of the building. What is point number 3? It's a tree. What is point number 4? The right-of-way. You know what I mean? What is 16 through 27? We'll probably just code those topo because that's just the land, okay? So the coding method that you use is going to be really important. I'm going to let your group decide how you want to organize that data. What we are ultimately going to have to do, though, is we're going to have to take your data and we're going to have to tweak the codes a little bit later on so that AutoCAD Civil 3D can interpret it the way that we want it to. So, like as an example, if you use the word TREE for all of your trees, then when you import it into AutoCAD Civil knows that's a tree, and it will use a tree symbol for those points, okay? So, but here's the other thing. AutoCAD is not going to know what a Coints court is, you know what I mean? So the way that we code that, we're actually going to define a Coints symbol, and then when we import our Coints data, it will go, oh, here's the 8 Coints ports, here's your symbols and whatnot. It will do a lot of the work for us. So we'll have to do a little bit of that later, okay? So when you're looking at the land, some key data, so you want to try and get all your high points, all your low points, any valley profiles or ridge profiles. So when we look at Buskirk, you know how like there's really only like that one hill on Buskirk? So you'll want to get data along the bottom of that hill, you'll want to get data along the top of that hill, and maybe a few intermediate points inside it so that you can get better relief along the hill. And we're going to kind of look at what your final answer will look like here in a bit. Okay? Any questions so far? Now I'm going to let you a little bit into the background on how the sausage is made from a computational perspective. So again, like the hand method is essentially taking your points and trying to identify visually, you know, where the contours are. What a computer's not doing that, okay? What a computer is going to do is it's going to take all of the data that you collect and it's going to generate a network, a grid of a grid network between the points that you collect, and it's going to use a series of algorithms and whatnot to identify where the contours are. So one of the points worth mentioning is that, you know, maybe when you do this by hand, like here or up here, your contours are going to be kind of smooth, whereas when you do it by a computer, your contours may be a little jagged. They may have some sharp edges to it. This is one of those things where the more data that you collect, the better contour you're going to get, because the more resolution that you're going to have in your network. Okay, and this is the same example that we were looking at here. I just took this end of it, and so here's the answer, right? So like I said, I wasn't going to do all of them, but you can kind of see what it's going to look like. We only did, you know, these points right here. I ignored the little triangular regions right here. But yeah, this is like one of the more classical methods in earthwork class. Does that make sense? Okay. All right. So what a software package will essentially do is it will take the points that you collect and it will try and generate what's called a triangulated irregular network, or a TIN. And so you actually could probably see that on that app I just showed you, because if you take that scan and try and export it, it will try and export it in a couple different formats, and one of them is a 10 file. And so basically what it's going to do is that there's an algorithm that the program will use to connect these points in such that we have sort of like near equilateral triangles between them. And we like equilateral triangles because it makes the generation of contours a lot easier. I just mentioned 10 files and whatnot, because that's how it works. Now, triangulated networks are not anything new. The algorithm actually to generate them is pretty straightforward, but it's been around for a very long time. Basically, the idea is that you generate a series of circular regions among a series of points, and the idea is that no point is inside a certain circle of any triangle. What was and the best way of actually understanding this is to actually see it in action. So if I go back to this and let's close this and let's do it again, so you can see what's happening. You can see the triangles and whatnot being generated. The more data, the better the mesh is. Does that make sense? And so you can see what it's doing. So I'm not going to get too far into the sausage on this because I don't want to get too far into mapping land or GIS land. I just kind of want to mention it. I do, however, want to talk about this. So I want everybody to take a good long look at this picture, okay? Because that yellow region, that's your boundary. That's what I want a topo of. I want a topo of this region, okay? I want a topo of this entirety of Buskirk Field, including the sidewalk, so we can see the coins courts right here. We can see CP 10, 11, 12, and 13. I do want you to shoot all the control points. So the sidewalks, the trees, and probably some area that you want to spend some time on is this hill, because this is the one area that has some slope on it. And I want you to bound this sidewalk here. So if you shoot all of this and all of this, this is the area that you're going to be constructing a topographic map for. Okay. What'll happen inside the background is that the more points that you collect, AutoCAD will generate a 10 network from the data that you collect. And yes, this was generated in MATLAB. Yes, this was generated in MATLAB. But what it's going to do, here's what it's doing. It's taking this triangulated network and it's essentially doing this to take this network and generate this. Okay, this is a relief contour of this area of campus, and you can see the contours are getting a little closer together over here because this is where we got that slope. Okay, when it's all said and done, you'll generate something that looks like this. This is more, if I'm being honest, this is more aligned with what I expect you to generate in this class, because I'm more interested in the science being accurate. So I want to be clear, this is kind of what I'm expecting, but this is a little bit more real world. Okay, this is about what you would really expect in the real world. And again, but the point I'm making is that this and this are both generated the same way. It's the same process, just a little bit more time went into this for the hatching and the aesthetics of it, as it were. This is a much more professional site plan generation that you would do. And this is very representative of what you would generate in the real world, whether you're in civil engineering or surveying. I've generated plats like this multiple times, especially when I was doing ALTA surveys and we had to generate plots of shopping centers and whatnot. It would not be uncommon that we would generate maps like this. This is what you would be doing professionally. But the point is, if you can do this, you can do this. I promise you. Okay? It's just more time. Okay? That's all it is. More time, more detail. Okay? Does anybody have any questions about the general idea? Okay? Okay, so let's just make sure we're clear on the logistics. Okay? So what we're going to be doing this week is we're going to be doing topo. Okay? I want you to collect as much data as possible. One thing I want to mention to the class is, and this is totally fine when you're doing a traverse. So when you're doing a traverse, there is much more, because I want to give you my advice on the lab going well, because I've been doing this for a long time. When you're doing a traverse, there is much more concern in ensuring you're writing down the right data, taking down the right measurements and whatnot, because you're going to have to compute with those later, and that I understand. But I want to give you some advice for how to do the topo lab. The first thing I would give you some advice on is make sure that you're taking proper note-taking, not so much on the distances and angles that you're measuring, because you're actually not going to write any of that down. You're going to let the total station collect all that data. Okay? Instead, on your note-taking side, I want you to make sure that you're doing a good job marking which points correspond to what feature. Okay? So, for example, if you take a shot of a manhole, or a stormwater drain, make sure that point number 17, that you've coded that appropriately and that you've noted that in your notes. That's what's really important, okay? That would be the first thing I would mention. The second thing I would mention, and I'm going to refer to the group, but for the folks on the YouTube recording who are like, why did Dr. Michelson do cacaw? We have a lab group that's how they signal how they're done with a shot, is they've done that. And while it's really funny, there's actually some genius to it because they know they're done, okay? Somebody's gonna be running the instrument, okay? And the other person is gonna be running all across Buskirk Field collecting all this different data. If they're just standing there, not knowing what's going on, then you're gonna be out there for a while, okay? Point blank. So you want to make sure that you within your group are developing a good communication strategy for somebody that's 500 feet away. And sometimes doing this might not be enough, okay? Because if you're sitting there looking at the bubble, making sure that the rod is level, you're not looking up for the person running the instrument doing this, okay? And I think normally land surveying professors talk about this at the very beginning of class. I actually waited to talk about it now because now that you've been out in the lab a little bit, I think probably some of you know what I'm talking about, right? That you're out there, you're trying to focus on running the instrument, that there's a communication aspect to it as well. I'm not saying like scream bloody murder, but you are outside. You can use your outdoor voices a little bit. You can, say good, use your outdoor voice and say that you're good. Make sure that the person out there knows. And the reason I'm saying this is because I want you to collect the data as expeditiously as possible. I mean, if you're at the point where you're collecting the topo points and it's taking you like 5 or 10 minutes to collect every point, you're doing something wrong. You should be able to go, set the rod down, person shoots. Good. Okay, move on. Like that's like you should be trying to get into that rhythm. Okay? I'm not saying you should do it that fast. I'm not expecting you to do it that fast as students, but I'm saying like as somebody who's surveyed in the field, when I've done topo jobs, like I collect the data, I set that rod, I move on. Like I'm never at one point more than 30 or 40 seconds, We have a really good communication strategy in our team. We know when somebody says something, it means something else. And I want you all to develop that as well. Again, because I don't want you to be out there to 6, 7 o'clock at night collecting data. Because on this lab, we're going to stop at 4:50 because we've got a whole nother week. Okay, that's sort of the idea. Make sense? Okay. All right. Any questions? All right, y'all got a little bit of time. I'll meet the Wednesday lab at 2 o'clock in 2241. With that, I'll see the Thursday lab tomorrow. And I'll pull the code up one more time. Let me stop the recording.